In this video, we will be learning the next controller, that is the integral controller. The block diagram of integral controller can be written as like this one. Seeing the different terminologies here, we will be giving the reference input given by R of t, and we will be having the feedback signal B of t coming from the client output here. Now, the feedback signal and the reference input gets added up at the summing point, which gives us any difference between this one, the reference input, and the feedback signal will give rise to error signal. Any difference between these two will resulting in the formation of the error signal. Now this error signal is fed as an input to our integral controller, which is having a gain constant or the transfer function given by k suffix I here. Now this integral controller, after processing this or getting the error signal as the input, it gives us the manipulated output given by m of t. Now looking at the relationship between the output and input of this integral controller, this mathematically we will be writing the equation as time differential of the manipulated output is equal to the gain constant or the integral gain constant ki into multiplied by the whatever the error signal which is fed as the input to the integral controller here. So the relationship between the manipulated output is nothing but the output and the input of the integral controller can be written or can be represented by using this equation. Now on integrating this equation, the LHS turns out to be m of t. This is equal to, on the RHS part we will be having ki, since it is a constant, we will not be applying any integral to this one, and e of t is nothing but the error signal which changes with respect to time, hence we will be integrating this with respect to time dt now. Now on integrating, we will be getting on the LHS this expression now. Now we will be applying the Laplace transform on both the LHS and RHS of this integral equation now here, so that we will be converting all these variables from the time domain to frequency domain here. On the LHS part, we will be writing this m of t as m of s. This is equal to k is a constant, so we will not be retaining as it is. Now we have this integral which is containing this e of t into dt. Now how to remember this one? This integral and multiplied by dt. Now whenever you are converting, applying the Laplace transform, that integral into dt will be written as 1 by s or reciprocal of s, and this e of t will be writing it as capital E of s. There is nothing but we will be changing from time to frequency here. Now rearranging this one, our gain constant ki can be written as s multiplied by m of s divided by E of s. This is the final equation that represents the relationship between the output to the input of the integral, the controller here. Now talking about the characteristics, this integral controller gives the engineering system wherever it is used can be listed as this one. First one, it slows down the system response. Now how it slows down? Since our manipulated output, it is very evident from this equation, since our manipulated output is time derivative of the manipulated output is dependent on the any changes in the input, our output obviously slows down whenever our input keeps on changing with respect to time. This is the evident, and we will be writing this as it slows down the response of the system with respect to any changes in the input of the system. That is nothing but the whatever the input that is fed to the controller of the system. And second is, it increases the setting time and the rise time of the system. This setting time and rise time are nothing but time taken by the system to reach the desired output which the system is designed for. This is all about the block diagram, the mathematical expression or the relationship between the output and input of the integral controller, as well as the characteristics this controller gives our engineering control system.